Any fluid knows complex analysis better than you. Take the Cauchy-Riemann equations, for example. For you, this is just something your professor told you about. But for a fluid, they are two physical properties. In this video, I will explain what the connection actually is, and how the Cauchy-Riemann equations could be derived directly from the properties of the fluid. But for that, let's ask a real expert, the fluid itself. As we know, fluids flow, and at every point, the fluid has a velocity. Let's call this velocity f. It has a horizontal component u and a vertical component v. The first condition we impose on the fluid is incompressibility. Very simple. What flows in must flow out. Nothing gets crumpled out in the middle, leaks away or vanishes suddenly. To feel this mathematically, let's take some region omega and compute how much flows into it and how much flows out. For this we compute the integral over the boundary of the region, but by the divergence theorem, this is just an integral over volume. Since this is true for every region, the integrand itself must be zero, and therefore the divergence is zero. Let's remember that. Now let's take a look at the second property. The second property guarantees that the flow is irrotational, and this means that if we move slightly forward, tiny vertices do not appear. To see this, we can simply put a tiny right angle to the fluid, and watch how it moves. It should move in such a way that the two sides of the angle do not rotate relative to each other. Let's write down the angular velocity of this little corner. It must be equal to zero. And importantly, this is instantaneous velocity. We set it equal to zero and remember this equation too. So now we obtained two equations, but if you look carefully, these are not exactly the Cauchy-Riemann equations for the analytic function f, but these are the Cauchy-Riemann equations for the analytic function conjugate f. And this is a very fundamental fact. The integral over such a conjugate function is called the complex potential. It is precisely a quantity that describes stationary and rotational flow of the incompressible fluid. For example, this is how the flows corresponding to different potentials look like. If you want to know how the fluids can solve the exterior Neumann problem, subscribe.